We engineer modern cars to be incredibly perceptive, bristling with optical cameras, radar, and LiDAR to scan the road ahead. But no matter how advanced these sensors get, they share the exact same biological limitation as the human eye. They require an unobstructed line of sight to work. A delivery truck parked on a crosswalk or a brick building obscuring a blind corner renders the most sophisticated autonomous vehicle completely blind to what is coming next. This chart visualizes annual traffic crashes, and the toll of that specific blind spot is staggering. The National Highway Traffic Safety Administration estimates that at least 439,000 crashes occur every year, simply because a driver or a sensor could not see the hazard in time. Solving this requires giving vehicles a digital sixth sense, vehicle-to-everything technology, or V2X. It allows cars to penetrate physical barriers and predict hazards well before they enter a camera's frame. To actually engineer traffic fatalities out of existence, the automotive industry has to move past reacting to what is visible and start predicting the invisible through continuous data sharing. The first and most critical layer of this network happens on the highway, where speeds leave zero margin for error. This is vehicle-to-vehicle communication, or V2V. This vector schematic shows how V2V enables cars to constantly talk to each other. The lead vehicle broadcasts a basic safety message containing its exact speed, position, and braking status up to 10 times a second. Now imagine a hazard. Heavy fog rolls in, obscuring visibility, and the lead car suddenly slams on its brakes. Standard optical sensors would fail here, likely resulting in a pileup because the third car cannot see the first. But with V2V, that third car receives the lead car's deceleration data instantly. The trailing car automatically initiates its own braking sequence milliseconds before the human driver even perceives a faint red glow through the mist. Bypassing the need for visual confirmation entirely eliminates the delayed reaction physics that cause multi-car pileups. Moving off the highway and into a busy urban environment, the network expands to the most dangerous geometric choke point on the road, the intersection. This is vehicle-to-infrastructure, or V2I. Here, the street itself is active. Traffic lights and municipal signs actively broadcast their operational status and timing cycles directly to approaching vehicle computers. Consider a high-stakes scenario where a human driver, obscured by tight building corners, approaches at high speed and blows through a solid red light. The intersection's V2I transmitter detects that incoming violation immediately. It sends an instant warning to the perpendicular cross traffic to halt, physically overriding their green light before they enter the crash zone. By connecting the infrastructure directly to the engine, V2I removes the most volatile variable from intersection collisions: human disobedience. The final physical layer accounts for the most vulnerable users of a dense streetscape. This is vehicle-to-pedestrian communication, or V2P. Pedestrians and cyclists participate in this exact same network by broadcasting their location and trajectory data via their smartphones or wearable devices. If a pedestrian steps out from between two parked vans to cross the street, they remain completely hidden from an oncoming car's optical sensors until it is too late. V2P prevents the physical strike by triggering the car's emergency braking system, based entirely on a digital handshake in the background, circumventing the need for a delayed visual confirmation. All of this raises a massive engineering question. How do hundreds of cars and devices constantly exchange this volume of spatial data without fatal network lag? The solution is the underlying technological engine of V2X, known as the PC5 Direct Interface. This comparison diagram shows exactly how PC5 solves the latency problem. Instead of routing data from a car up to a cell tower and back down to another vehicle, the PC5 protocol bypasses distant cell towers entirely, allowing devices to talk to each other locally. It operates on dedicated 5.9 GHz frequency bands, ensuring that even in dense bumper-to-bumper traffic, the communication remains reliable and uninterrupted. Eliminating the cloud from the loop and keeping data transmissions strictly local is the only mathematical way to process hazard information faster than human neurological reaction times. This illustration of a sprawling city grid shows the end result: a fully integrated V2X ecosystem functioning in real time. Historically, automotive safety focused entirely on protecting a single occupant inside an isolated, armor-plated box using seatbelts and airbags. Today, this interconnected web of data acts as a shared immunity system for the road, and it is the hard prerequisite for the widespread adoption of fully autonomous driving. Self-driving vehicles can only execute complex group maneuvers, like tight platooning at highway speeds, when they can anticipate the physical environment far beyond the reach of their own local sensors. The future vehicle operates as an active, talking node in a synchronized ecosystem, shifting the priority from surviving a crash to preventing it from ever happening in the first place.